in the last lecture we have started to discuss the ideal Bose gas. Actually, we have compared the ideal Bose gas with ideal Boltzmann gas in the previous lecture. In fact, now we are going to discuss the same problem, but our aim is to deal with particularly the thermodynamic behavior of an ideal Bose gas in two conditions of temperature. First of all, we will see the different thermodynamic behavior of an ideal Bose gas when the temperature of the gas is less than the critical temperature. And after that, we will discuss the behavior of the same ideal Bose gas but when its temperature is greater than critical temperature. Actually, temperature plays a vital role in affecting the thermodynamic property or thermodynamic behavior of an ideal Bose gas. Okay. So I have divided this lecture on thermodynamic behavior of an ideal Bose gas in three parts. In first part, which we will see here, we will only find what will be the expression for the critical temperature, what will be the expression for the energy of the gas and the number of bosons or number of particles in this gas. Only these basic equations we will find in this first lecture. Actually, after getting these results, we will be able to deal with the thermodynamic behavior of the ideal Bose gas in two different temperature conditions. As I have told you that first of all, we will discuss the thermodynamic behavior of the ideal gas when temperature of the gas T is less than critical temperature Tc, and then in next lecture, that is in final lecture, we will discuss the same problem when T will be greater than Tc. So actually in these two conditions we will discuss the different thermodynamic behavior of an ideal Bose gas. Okay. So actually this discussion is also limited in a particular limiting condition. As I have mentioned it here, you can see what is the purpose of this lecture. Already you have discussed the ideal Bose gas, then why we are going to deal with this particular lecture. Actually, aim of this lecture is to know about the physical behavior of an ideal Bose gas in a particular condition. And that particular condition is what? That particular condition is e to the power mu by kt is much smaller than 1. In fact, in this limiting condition is known as Boltzmann limit. So in Boltzmann limit, our aim is to investigate the physical behavior of an ideal Bose gas. Actually, when you will consider this particular condition that this e to the power mu by kt is much smaller than 1, you know mu is the chemical potential of the gas, which is called Boltzmann limit, then we will be actually able to compare the results for the ideal Bose gas and the ideal Boltzmann gas. So in this particular Boltzmann limiting condition, our discussion will be limited. Okay. As I have told you that in this particular lecture, we will not see the different thermodynamic properties of the ideal Bose gas, but we will only derive the fundamental equations needed for the discussion of thermodynamical behavior of an ideal Bose gas in this lecture. Okay. And for this, let us consider there is a system of n particles and all those n particles are bosons, that is the particles of the system obey the Bose-Einstein distribution law. Okay. And as you know that in this system, generally there will be two energy levels. The lowest energy level, in which the energy is assumed to be zero, is called ground level or ground state, and the another energy level when energy of the system is not zero, that is called excited state. Okay, so this is your ground state, GS you can say, and this is ES, that is excited state. And at a particular temperature T, let us consider that in this ground state, the number of bosons or the number of particles of this system is equal to N0. And in this excited state, we consider that the number of particles or number of bosons is equal to Ne. We consider, okay. This N0 represents the number of particles in ground state, that is in a state where E is equal to 0, and Ne is the number of particles in excited state when E is not equal to 0. As the total number of particles is N, so you can easily say that this N0 plus Ne will be equal to N. Okay, and that's why you can also say that this number of particles Ne is simply equal to N minus N0. Okay. Now, actually, before this lecture, we have discussed so many results for this bosonic system. But as I have told you that our discussion is limited here in this limiting condition, that we consider the condition that e to the power mu by kt is much smaller than 1. Actually, when e to the power mu by kt is much smaller than 1, when this will be possible, you can think. Actually, when as you know that this mu, which is chemical potential of the gas, and you know that chemical potential for Bose gas is always negative. It is always negative. Okay. So this e to the power mu by kt is definitely smaller than 1. Okay. But when this t will be very large, in that condition, this number e to the power mu by kt will be much smaller than 1. Okay. And in fact, in this condition, the number of particles in ground state is negligible. Almost no particles are found in the ground state. When there will be almost negligible number of particles in ground state, what will happen? Actually, in that very condition, almost all particles will be in the excited state. So you can say that when this condition is satisfied, that is e to the power mu by kt is much smaller than 1, then the number of particles in excited state, that is Ne, is almost equal to N. That is the total number of particles. Okay, and the ground state is almost empty. But let us think, what will happen when you increases the temperature. Okay, so as the temperature increases, in fact, in that condition, this e to the power mu by kt will increase. E to the power mu by kt will increase, and it will be never greater than 1. So at very high temperature, when this e to the power mu by kt will tend towards 1. Actually, this is the maximum value of e to the power mu by kt. It is never greater than 1. Okay. So in this condition, when e to the power mu by kt tends towards 1, that is e to the power mu by kt is at its maximum value, then actually a significant number of particles are found in the ground state. That is, in this condition, this N0, which is number of particles in ground state, has a significant value. You can't neglect it. Okay? And in this condition, as there will be two phases of the gas will be found in the excited state and also it is found in the ground state. So in this condition, the behavior of this system is significantly different from the classical ideal gas, or you can say the Boltzmann gas. Okay, so at high temperature, you will see later on when this mu by e to the power mu by kT is much smaller than 1. In fact, in that condition, almost all particles are in excited state, and you will see later on that in this condition, this ideal Bose gas will behave just like a Boltzmann gas. Okay? But when temperature decreases, then the value of this number e to the power mu by kT increases and it tends towards 1, which is its maximum value. And in this condition, there will be a significant number of particles in the ground state, and in that very condition, the behavior of the ideal Bose gas is very different from the Boltzmann gas. Okay? All these things will be clear to you in the forthcoming lecture when we will actually calculate the different thermodynamic properties for ideal Bose gas, and we will compare to the same value, same quantity for the Boltzmann gas. Okay? Now, as you know that the Bose gas consists of bosons, and bosons have integral spin which may be 0, 1, 2, 3 and so on. In this discussion, for simplicity, we consider that our ideal Bose gas is consisted of spinless bosons or spinless particles. This is for simplicity only. When you say that your gas is composed of spinless particles, it means the spin quantum number s equal to 0 for the particles of the gas or for the bosons. And you know that the spin degeneracy factor Gs, which is equal to 2s plus 1, but since s is 0, so this will be 2 into 0 plus 1, that is 1. So, in this discussion, we consider that the spin degeneracy factor Gs is equal to 1 for our system. Okay? And as you have learnt in the previous lecture on ideal Bose gas, some of the important results. So, all those results which we have studied earlier in very detail and derived those results I will write here directly. So I am writing here that the number of particles in the excited state, which is equal to n minus n0. We have learnt in the previous lecture that this is equal to 2 pi v over h cube times 2m to the power 3 by 2 and integral 0 to infinity e to the power half dE divided by A inverse e to the power e by kT minus 1. Actually, here you know that this A inverse, which is equal to 1 by A, this is equal to e to the power minus alpha. Okay? This result I have written directly because you have learnt this result in the previous lecture. Okay? And in the similar manner, you can also write the expression for the total energy of this system, which is given by 2 pi v over h cube times 2m to the power 3 by 2 integral from 0 to infinity e to the power 3 by 2 dE divided by A inverse e to the power e by kT minus 1. Okay. These two results I have written directly because you have learnt these results in the previous lecture. And for writing the answer in your examination, you have to remember it, because this is already a very lengthy concept where the answer will be very lengthy. So you should definitely remember these results and write here directly. Okay. Now we will try to evaluate these two integrals in equation 1 and 2. Although in the previous discussion we have already evaluated these integrals, but here I will try to evaluate these integrals in some other manner. Although result will be same, but some rigorous method here we are going to follow to evaluate these two integrals. And for this, let us consider that this factor E by kt is equal to epsilon. We consider it. You have also considered this fact previously. And so from here you can see that this differential of E will be equal to kt times differential of epsilon. Okay. Now, when you take E by kt equal to epsilon, you can see if if E is equal to 0, what will be epsilon? Epsilon will be also 0, you can see. And when E is equal to infinity, you can see epsilon will be also infinity. From this result you can see. And so the limits in these two integrals will not change when you will change the parameter E to epsilon. Okay. So in terms of this epsilon, the above two equations you can write like this. This n of E is equal to n minus n0 equal to 2 pi v times 2 pi m kt divided by h square to the power 3 by 2 and integral 0 to infinity epsilon to the power half d epsilon over A inverse e to the power epsilon minus 1. Okay. And similarly, the expression for the total energy of this gaseous system U is equal to 2 pi v times kt into 2m kt over h bar square whole to the power 3 by 2 and integral 0 to infinity epsilon to the power 3 by 2 d epsilon divided by A inverse e to the power epsilon minus 1. Okay. So these are the two results for NE and U. But now we will try to evaluate the integrals existing in this equation number 3 and in this equation 4. Already we have evaluated these two integrals in the previous lecture, but as I have told you, here I am going to follow or I am going to adopt a rigorous method, a very suitable and compact method to evaluate these integrals. Okay. Actually, we will evaluate these integrals in terms of gamma function. Okay. So when these two integrals will be evaluated in which actually appear in equation 3 and 4, what will be our result? I have written here directly, but you can see the different quantities are how defined. In fact, after evaluation, it is found that Ne will be equal to V by lambda cube times G by G3 by 2 of A. And the expression for U will become 3 by 2 kt times V over lambda to the power 5 times G5 by 2 of A. But what is this lambda? What is this G by 3, G3 by 2 and G5 by 2? Now, what are these? Now, let us see. Actually, this lambda, which is actually called thermal de Broglie wavelength, and that has been written at the place of h square over 2 pi m kt whole to the power half. Or you can also say that this lambda is equal to h over a square root of 2 pi m kt. Instead of this factor, this lambda has been written. Okay. And In general, this function g, this is defined like this is a function of a, and gn of a is defined like this. This is 1 over gamma n integral 0 to infinity epsilon to the power n minus 1 divided by a inverse e to the power epsilon minus 1 d epsilon. You can check. Actually, in the first equation for any in integral, there is power half on epsilon, and you can see that this gn of a, at the place of gn of a in equation 5, I have written g 3 by 2. So n is here 3 by 2. If n is 3 by 2, then what will be this epsilon to the power n minus 1? This will be epsilon to the power 3 by 2 minus 1. This will be epsilon to the power 1 by 2. Okay? And similarly, in the energy expression inside the integral, there is epsilon to the power 3 by 2. So you can see when n is equal to 5 by 2, then you have to write for the integral here, this will be in fact epsilon to the power 5 by 2 minus 1, which is epsilon to the power 3 by 2. So we can write this expression or these integrals in terms of the gamma function like this. So gn of a is defined as 1 over gamma n integral 0 to infinity epsilon n minus 1 divided by a inverse e to the power epsilon minus 1 d epsilon. Okay, and this gamma n, as you know, this is called gamma function. Okay, so in terms of gamma function, you can find the value of these integrals. Okay, and after this you can express, if your aim is to find the integral, definitely first of all we have to evaluate 1 over this 1, this will be 1 over, see here, 1 over a inverse e to the power epsilon minus 1. Okay, first of all we have to evaluate. We have to actually expand this in power series. You can see actually our consideration is that a is very small, because you have written a instead of what? A is equal to e to the power mu by kt, and we have considered that this is much smaller than 1, so a is very small. So taking the value of a much smaller, when we will try to expand this, what will be our result? Actually, this expansion has been already done previously. You can see this can be written as a inverse e to the power epsilon minus 1 whole to the power minus 1. Now we take the first term a inverse e to the power epsilon as a common factor, since it is inside, since there is a minus 1 power on whole. So when you will take it outside of the bracket, this will be a e to the power minus epsilon. Okay, and times 1 minus 1 by this much and 1 by this much will be equal to what? That will be a e to the power minus 1 and to the power minus 1. Okay. Now this is just in the form of 1 minus x to the power minus 1, and when you will make the binomial expansion, this will be what? This will be 1 plus x square plus x cube and plus so on. Here at the place of x you can see there is a times e to the power minus epsilon. So using this binomial expansion you can write that this is equal to 1 plus a e to the power minus 1 plus a square e to the power minus 2 epsilon and so on. So when you will actually multiply the terms inside the bracket by this a e to the power minus epsilon, your result will be what? This is a e to the power minus epsilon plus a square e to the power minus 2 epsilon plus a cube e to the power minus 3 epsilon, okay, and so on. And this can be written in compact form like this. This can be written as summation over L from 1 to infinity, you can see a to the power L times e to the power minus L epsilon. Can you write like this or not? Definitely you can see. When you will put the limit, you will get this series actually. So this 1 over a inverse e to the power epsilon minus 1, under the condition that value of a is smaller, this can be written like this, which I have written here. Okay. So now to find the value of this function gn of a, you can use this value of 1 over a inverse e to the power epsilon minus 1. So you can see as gn of a is equal to this much, which I have defined in this equation number 8. So you can see that instead of this we will write which we have just obtained. So after substituting this value, what will be your result? You can see gn of a will be equal to 1 over gamma n times summation over L 1 to infinity a to the power L times integral 0 to infinity e to the power minus L epsilon times e epsilon to the power n minus 1 d epsilon. Okay. Now this can be written as gn of a equal to summation over L 1 to infinity a to the power L divided by L to the power n. Okay, a to the power L divided by L to the power n. Okay, and so this gn of a, when you will put the limit, let us see what will be the result. Let us put L equal to 1. So this will be a to the power 1, that is a, and divided by 1 to the power n, which will be 1. So the first term is a. Now L equal to 2, so there will be a square divided by 2 to the power n plus L equal to now 3. This is a cube divided by 3 to the power n and so on. So this gn of a is equal to this much. You can also take this a as a common factor. Actually, I have denoted this this term earlier by f of alpha. Okay. Now, as I have told you earlier that for a Bose gas, the chemical potential is always negative. The chemical potential of Bose gas is always negative, and as its chemical potential is always negative, so you can see that this A is, which is equal to e to the power alpha, and alpha is equal to mu by kt. So this A is equal to e to the power mu by kt. This will be definitely less or equal to 1. Okay. And when this temperature T is lowered, as I have told you earlier too, when T will be lowered, then the value of A will increase, and its maximum value can be only 1. It is never greater than 1. So on increasing on decreasing the temperature, the value of A starts increasing from 0 to its maximum value, which is equal to 1. Okay? When this A is maximum, in fact, in that condition, temperature is very small, and that particular temperature, when this A becomes 1, is known as critical temperature. Okay? So, critical temperature is the temperature when this parameter A or e to the power mu by kT is equal to 1. Okay? That becomes 1. And that temperature is called actually the critical temperature. So I have mentioned it here. You can see that the maximum value A equal to 1 is reached at T equal to Tc, which is called critical temperature. Okay. Now, if you want to find the value of this critical temperature Tc, then you can use this equation 5, which you have learnt earlier. Actually, by the use of this equation 5, we can find the value of Tc, and for this you will have to put A equal to 1. So Ne will be V divided by lambda cube G 3 by 2 1, because you have to take 1, because when you will take A equal to 1, then you have to write T equal to Tc, and in that condition the lambda will be what? Lambda will be actually h divided by 2 pi square root of 2 pi m k Tc, not T. Okay? So in the value of lambda, this T will be replaced by Tc because A is equal to 1, and in that condition, when A is 1, T becomes Tc, which is critical temperature. So on substituting the value of lambda, what will be actually the critical temperature we can easily obtain. So you can see that the number of particles n, actually in this condition, this Ne is almost equal to n. Almost equal to n. It means at a temperature above than the critical temperature, almost all particles of this system are found in the excited state. Okay? And all particles are found in excited state, and there is no particle in the ground state. Almost. Okay? This is equal to 0. So instead of Ne in equation 5, we will write simply n, and here actually value of lambda has been substituted, and you have seen that in that expression there was 1 by lambda cube, and lambda has been defined already. So after substituting the value of 1 by lambda cube, you will see your result will be 2 pi m k Tc divided by h square whole to the power 3 by 2 into V times zeta 3 by 2. Actually here a new function zeta 3 by 2 has been introduced. In fact, this zeta 3 by 2 is simply equal to g 3 by 2 of 1. Okay? g 3 by 2 of 1. Actually, this is called Riemann zeta function. Okay? And what will be actually the value of this zeta 3 by 2 or g 3 by 2 1? 1 here is for A, and you can see in the general value of Gn of A is defined in this equation 1. So in this equation 9. So from here you can easily find that what will be G3 by 2 of 1. So here n will be equal to 3 by 2 and A is equal to 1. So substituting A equal to 1 and n equal to 3 by 2 in this equation 9, we can find G3 by 2 of 1, and G3 by 2 of 1 has been written as zeta 3 by 2, which is actually called Riemann zeta function. And you can see when you will substitute A equal to 1 and n equal to 3 by 2, that series will become 1 plus 1 over 2 by 2 to the power 3 by 2 plus 1 over 3 to the power 3 by 2 and so on. So this is actually the value of zeta 3 by 2. Okay, zeta 3 by 2. And from here you can easily find what will be this Tc. Tc can be obtained from this result. Okay, so here as I have written that this zeta of L, which is defined like this is summation over n 1 to infinity 1 by n to the power L. This function is called actually a Riemann zeta function. And from this result you can see if your aim is to find this Tc, what will be this Tc? The algebra is simple. You can see that this Tc will be equal to this much. This is n over zeta 3 by 2 times v whole to the power 2 by 3 times h square by 2 pi mk. This is actually the value of critical temperature. Actually, for all known Bose gases, this critical temperature is very low, very small. Always, for any Bose gas, critical temperature is very small. For example, you can remember that for helium-4, which is actually a boson or helium-4 particles constitute the Bose gas. For this gas, this critical temperature is 3.13 Kelvin. This I have stated earlier too. Okay. And as I have told you earlier, our aim is to discuss the thermodynamic properties or thermodynamic behavior of an ideal Bose gas in two different temperature conditions. First condition, I have told you that we will see the different thermodynamic property of Bose gas when temperature T is less than Tc, and the another situation will be when T is greater than Tc. In these two conditions, we will discuss the thermodynamic properties of an ideal Bose gas in the forthcoming lecture. This is our aim. So actually, when you will talk about this condition, T is less than Tc, that is in the region 0 less or equal to T less or equal to Tc, then you will see that this Bose gas shows some specific behavior, some peculiar behavior, and some peculiar behavior you have already discussed earlier, like Bose-Einstein condensation, okay, liquid helium. These are the different phenomena which occurs actually when temperature of gas is less than Tc. So this is the most important case when temperature of the gas is less than critical temperature. Then actually this Bose gas differs much from the ordinary Boltzmann gas, and it possesses some peculiar properties. But you will see also that when T is greater than Tc, then almost this Bose gas behaves like Boltzmann gas. Okay, but what are the values of different thermodynamic properties? How they are different from the ordinary classical gas? All these things will be discussed in the forthcoming lecture. Actually, in this next lecture, we will see the thermodynamic behavior of an ideal Bose gas when its temperature is less than Tc. And after that, in next lecture, we will discuss the same problem when T will be greater than Tc. So I hope you have definitely enjoyed this basic lecture on the thermodynamic behavior, but the second and third lecture will be more important, and that is actually the purpose of this lecture series. Okay, so thank you very much.